Now here is the most important view graph of today, and so I'm going to take some time to talk about this view graph. And this has two distinguished physicists on the right. At the very top is Max Planck. And in the year 1900, Max Planck published a formula for the blue smooth curve you see on the view graph. Now, what this view graph shows is it's the thermal radiation coming out to space through clear air, no clouds, versus frequency. So the frequency goes left to right, and for thermal radiation, you typically use the spatial frequency, the number of waves per centimeter, wave numbers they call it. And going up is watts per square meter, or maybe milliwatts per square meter per wave number. So that blue curve was actually known empirically. Lots of experimentalists had measured it in the late 1800s, but nobody could figure out what it was. And it was really completely at variance with classical physics. And thank goodness for that, because classical physics said this blue curve would go up to infinity as you go down to the origin. So it was called the ultraviolet catastrophe. You know, it was a real problem. And so the solution of this problem by Max Planck was really the invention of quantum mechanics. So a lot of people, when they talk about quantum mechanics, they think of, you know, accelerators and all sorts of things, but it really came from the study of heat radiation. That's what drove it. Now, if you look down at the Earth, you don't see this blue curve from a satellite. What you see is very close to this jagged black curve here, and I like to call that the Schwarzschild curve. Schwarzschild was a bit younger than Planck, another great German physicist. He died during World War I on the Russian front. You know, I thought at first the Russians had shot him, but no, he had some autoimmune disease that unfortunately he didn't get the right treatment in the, you know, conditions of the trenches there, and he died. But before he did amazing things. He was the first, for example, to solve Einstein's general theory of relativity, give an analytic solution to that. People still use it today. And he also showed how to account for the effects of greenhouse gases that we're talking about: carbon dioxide, water vapor, which is by far the most important greenhouse gas, methane. Now, you notice that the black curve, the area under the black curve is the amount of radiation that actually gets out to space and cools the Earth. So the more that area, the more the Earth cools. And it's only about 70% of the area under the blue curve. So greenhouse gases are definitely slowing the cooling of the Earth. There really is a greenhouse effect. It's quite substantial. Most of it's water, but a non-trivial amount of CO2. But the important point that I don't want you to forget today is, if you double CO2, what happens is you go from this jagged black curve to a jagged red curve, which is almost coincident. You can only see the difference between the red curve and the jagged black curve right in the bottom of the CO2 absorption emission band. And if you would actually put in the numbers here, you find that if you double CO2, 100% increase of CO2, you decrease radiation to space by 1%, at 1.1%, but one I'll use for convenience. So let that sink in. Huge effect, huge doubling, effect of doubling CO2, at least in the numbers of CO2 atoms. We're far from doubling it today. It'll take a long time. It only causes a 1% change. So CO2 is a very poor greenhouse gas. It's not an efficient greenhouse gas. And now let's see, if you take all the CO2 away, focus on this view graph again, you go to the green curve. So going from no CO2 at all gives you the green curve and the black curve. They coincide, except in the CO2 band. there's a huge effect of going from 0 CO2 to 400 parts per million, for which this calculation was done. But going to 800 parts per million, it almost doesn't matter. So you get all of the effect in the first little bit of added CO2. Now you could ask, how do you know that you know how to calculate correctly? And well, this is sort of my professional field, so if I know how to do anything, I know how to do this. But this is a comparison of what we calculate compared to what's observed. So on the right, you see some measured spectra of thermal radiation coming up to satellites. They've got interferometers there that do these measurements. They're beautifully calibrated. And on the left, you can see our model calculations. You really can't tell the difference. So there are not many parts of the climate narrative that you can actually do a calculation that is 1 or 2%, but this is one of them. You really can't make a mistake here. So it's really true that doubling CO2 only causes a 1% decrease of radiation. IPCC gets the same answer, so this is not really controversial, although they will never show you the curve or tell you that it's 1%. You know, that would interfere with